Today we are going to discuss about the chapter Electrochemistry, and so you would be able to describe an electrochemical cell, understand the electrode potential and EMF of a cell, and differentiate between galvanic and electrolytic cells after today's discussion. Electrochemistry finds its existence in theoretical as well as practical approaches. Right from the cells and batteries used in toy cars or robots or remote controls to your mobile phones and laptop batteries, and then to the processes like gold plating, electrochemistry can be explained everywhere. Electrochemistry is the branch of chemistry that deals with the relation between electrical and chemical transformations. There are two types of electrochemical cells which are used to make these transformations: electrolytic cells and galvanic cells. Electrolytic cells convert electrical energy into chemical energy with the help of an external source. Galvanic cells, which are also known as voltaic cells, converts chemical energy of spontaneous redox reaction into electrical energy. We will begin this discussion with the recapitulation of our previous understanding about the redox reactions. Redox reactions are the type of chemical reactions where reactants undergo changes in their oxidation states. Let us understand this with an example. When zinc reacts with copper ions, we get zinc ions plus copper metal. This reaction is a combination of two half reactions whose addition gives the overall cell reaction. Zn undergoing changes to Zn2 plus with the loss of 2 electrons, and copper 2 plus gaining those 2 electrons to give the copper. Zinc undergoes oxidation as it loses 2 electrons, while copper undergoes reduction as it gains 2 electrons. Since the electron exchange is occurring simultaneously, it is considered as a redox reaction. You can remember this concept with a simple trick as oil in rig, which means oxidation is loss of electrons and reduction is gain of electrons. In this redox reaction, if we make these electrons to flow, then we can generate electricity. Now the question arises, how can we do this? For this, we will have to have a redox reaction taking place in two separate containers or one container separated by a permeable membrane. We will also have to keep the potential difference between the two electrodes. Now, I will explain you what is the meaning of electrode potential. Let us take an example of zinc rod dipped in zinc sulfate solution. The zinc atoms have a tendency to lose electrons, and so it forms zinc 2 plus ions, which go into the solution as a result of oxidation. So the reaction becomes Zn giving Zn2 plus ions with the loss of 2 electrons. The electrons accumulate on the electrode and acquire a negative charge. The electrons present at the electrode will also have a tendency to attract the positive ions present in the solution. This leads to the separation of positive and negative charges. This further leads to a potential difference between the metal electrode and its ions present in the solution at equilibrium, and this is called electrode potential. It may also be considered as the tendency of the electrode to lose or gain electrons when it is in contact with the solution of its own ions. Electrode potential depends on nature of metal electrodes and the metal ions in the electrolyte. It also depends on the concentration of the ions and also on the temperature. The electrode potential when measured under standard conditions of temperature 298 Kelvin for 1 molar solution is called standard electrode potential and is denoted by E0. And if it is a gaseous electrode, pressure condition of 1 atmosphere is considered. According to IUPAC convention, standard reduction potentials are now called standard electrode potentials. The electrode which has low electrode potential has a tendency to get oxidized. Now let us combine the two concepts we have just learned for the generation of electricity. For this purpose, we will set up a cell which is called galvanic cell or voltaic cell. Let us now construct a galvanic cell. For the construction of a galvanic cell, we need two containers. One container consists of zinc plate dipped in zinc sulfate solution. The other container consists of copper plate in copper sulfate solution. The two containers are connected through the wires which are then connected through a multimeter. If you see, the connection is somewhere incomplete and that is why the multimeter is not reading any value. Here, the salt bridge comes to the rescue. We need a device called salt bridge. What is a salt bridge? A salt bridge is an inverted U-shaped glass tube which contains a relatively inert electrolyte, usually potassium chloride or sodium chloride or potassium nitrate solution. The electrolyte is often jellified with agar-agar to help prevent the intermixing of fluids and is then sealed with a cotton plug at the ends. A salt bridge helps in neutralizing the extra positive charge of the zinc ions present around the anode, with an equivalent amount of the anions migrated from the salt bridge, and similarly the equivalent amount of cations from the salt bridge neutralizes the negative charge of the extra sulfate ions present. Therefore, we may say that the salt bridge is used to complete the inner cell circuit. It also prevents the transference of electrolyte from one half cell to another. It maintains the charge balance or electrical neutrality of the electrolytes in the two half cells. This is a salt bridge which is made from a filter paper by dipping it in a saturated solution of potassium chloride. As soon as I introduce it as a bridge into the two containers, after inserting the salt bridge, when we connect the copper plates through the multimeter, we see that the readings have started to begin. The reading will reach up to 1.1 volts because the E0 cell of a galvanic cell is 1.1 volt. The fact that electrons flow from one electrode to another indicates that there is a potential difference between the two electrodes. This potential difference between the two electrodes under standard conditions when no current is drawn through the cell is called standard electromotive force or EMF of a cell and is denoted by E0 cell. It is measured by connecting a voltmeter in between the electrodes and is measured in volts. The value is given by the expression E0 cell is equal to E0 right minus E0 left, or we may also write it as E0 cell is equal to E0 cathode minus E0 anode. So, if we need to calculate the E0 cell of the galvanic cell, the electrode potential of zinc 2 plus to zinc from the table is minus 0.76 volt and that of copper 2 plus to copper is 0.34 volts. We can substitute the values in the expression as 0.34 minus 0.76, which gives us the value as 1.1 volt. If an external opposite potential is applied in the galvanic cell and increased slowly, we find that the reaction continues to take place. Once the opposing voltage reaches the value 1.1 volt, the reaction stops altogether and no current flows through the cell. Any further increase in the external potential again starts the reaction, but in the opposite direction. An electrochemical cell may be represented by using internationally accepted conventions. The metal electrode in the oxidation half cell is represented by its symbol, which is followed by its metal ions along with its concentration. They are separated by a vertical line. So, for the zinc electrode, we will write it as zinc, vertical line, zinc 2 plus ions, and in the concentration we will write 1 molar. Similarly, the metal ion in the reduction half cell is represented by its symbol along with its concentration, and this is followed by its metal electrode. They are separated by a vertical line. For copper electrode, we will write it as copper ions, 1 molar concentration, vertical line, copper. The salt bridge separating the two half cells is represented by 2 vertical lines. So, the final representation of the cell looks like Zn, vertical line, zinc ions, 1 molar concentration, double vertical lines, copper ions, 1 molar concentration, single vertical line, copper. You may remember the setup of galvanic cell with a trick, the word lone, which stands for left, oxidation, anode and negative. Hence, you may realize that we have converted the chemical energy into electrical energy with the help of an electrochemical cell. Also, we may now differentiate between the two types of electrochemical cells, galvanic cells and electrolytic cells. Galvanic cells changes chemical energy into electrical energy, while electrolytic cell changes electrical energy into chemical reaction. The anode is negative in a galvanic cell, while in electrolytic cell it is positive. The cathode is positive in galvanic cell, but it is negative in an electrolytic cell. Galvanic cell requires spontaneous reactions, while electrolytic cells require non-spontaneous reactions. Galvanic cell does not require external voltage source, but an electrolytic cell requires external voltage source. So, let us summarize our discussion with a concept map. Electrochemistry is a branch of chemistry which is based on redox reactions. The redox reactions involve the process of oxidation and reduction. The chemical energy generated by these redox reactions is converted into electrical energy by a galvanic cell, and electrical energy is converted into chemical energy by an electrolytic cell. The galvanic cell can be further explained through 2 electrodes, anode and cathode. In anode, we may describe the concept of lone as left electrode undergoes oxidation and is referred as anode and bears negative charge, and the opposite follows for the cathode. So, the right electrode will have reduction happening in it, will be called cathode and will possess a positive charge. The electrons are released from the anode due to its low standard electrode potential. In cathode, electrons are accumulated or absorbed due to its high standard electrode potential. The flow of electrons occurs from anode to cathode and flow of ions occurs from cathode to anode and the whole circuit gets complete. Also, the flow of electrons and flow of current is monitored in the opposite directions to each other. I hope you understood all the concepts explained in this discussion. Before we conclude today's discussion, I would like to leave you all with an assignment. You may create your own electrochemical cell at home by simply replacing the electrolytic containers with any citrus fruits such as lemon or orange and then connect it to a bell. The circuit will be considered connected once the bell starts ringing. This way, you will also be able to help your visually impaired friends to understand the concept of an electrochemical cell.